This is 2.1.2. Stable and unstable nuclei.
Oh, wait, two. Are you recording this?
Now, the first thing you need to do is you need to learn the typical sizes of atoms and nuclei. Now, when I say typical sizes, I'm not saying that every single atom has the exact same size. What I am telling you is the order of magnitude of their sizes. So what do I mean by an order of magnitude? For example, if we think of common vehicles on the road, their order of magnitude is in the thousands of kilograms. So they're 10 to the 3. So typical values would be 1,000, 2,000, 3,000 for a particularly heavy vehicle. But you won't expect something like 50,000, because that's an order of magnitude off. You won't expect vehicles like cars to be 100 kilograms. Again, that's an order of magnitude off. So I'm giving you an order of magnitude, but there is variation because nuclei come in different sizes and atoms come in different sizes depending on how much stuff they have. So we draw an arbitrary nucleus. Arbitrary means random, without any thought into how much stuff is actually in there. And then we'll just randomly shade in certain parts to illustrate that some are protons, some are neutrons. Again, the number doesn't matter, we're just illustrating this. Then I'm going to draw just one set of electrons, again just arbitrarily, to show an illustration of an atom. Now, the typical size we have for an atom is roughly 10 to the minus 10 meters, also called an angstrom. The diameter for the nucleus is 10 to the minus 15 meters, and we call that a femtometer. So let's write atom is an angstrom, which is roughly 10 to the minus 10 meters, and the nucleus is a femtometer, which is roughly 10 to the minus 15 meters. Well, not roughly, femto means 10 to the minus 15, but it's in that order of magnitude. So 1 times 10 to the minus 15, 2 times 10 to the minus 15, 3.6 times 10 to the minus 15. These are the kind of numbers you expect. Next, we'll talk about the strong nuclear force, which is the new fundamental force that you need to know about. So in an atom, we have protons, which are positively charged. Positive charges should repel each other. So just by considering the electromagnetic force only, nuclei should not exist. Because so far we haven't looked at things or force that keeps things together, that's attractive. So we actually have two forces at play here. So protons in the nucleus repel each other due to being positively charged. And that is the electromagnetic force. Now, every proton in the nucleus repels every other proton. Even if you have a very, very big nucleus and one proton is on one side of the nucleus, the other proton is all the way on the other side, they still repel each other. But there's another force which is acting, which is an attractive force, called the strong nuclear force. So the strong nuclear force is a short-range force, but I'll add in there a short-range attractive force that acts between nucleons. So notice I didn't say protons, I said nucleons. That includes the neutrons. So electromagnetically, neutrons are neutral, they have no charge. If they have no charge, they cannot repel, they cannot attract the protons. But because they're also nucleons, the neutrons also experience a strong nuclear force, so they do experience the attraction, they don't experience any of the repulsion. But the strong nuclear force is very short range. So the electromagnetic force pretty much has an infinite range. Even if the two protons are on opposite sides of that nucleus, they will repel each other. They don't have to be next door neighbors. But the strong nuclear force, it can't act at very long ranges. So a proton that's all the way on one side, a proton that's all the way on the other side, there won't be an attraction between their strong nuclear force. So the rough separations, we have a proton and another proton, would be roughly 3 femtometers at a maximum value. So we say that between 0.5 femtometers to 3 femtometers, the strong nuclear force, I'm going to put SNF for short, is attractive. Less than 0.5 femtometers, the strong nuclear force actually becomes repulsive. So what happens there is, yes, you attract the protons and neutrons together, you keep them bound in the nucleus, but you don't bring them too close together. You stop them from collapsing on each other and fusing together. So that keeps the nucleus stable. Because if these particles start collapsing onto each other, then they'll cease to exist and start forming different particles instead. And if you're further than 3 femtometers, then the strong nuclear force is negligible. Pretty much doesn't exist. So at greater than 3 femtometers, the strong nuclear force is negligible. Now if we graph what this looks like, we have a graph which looks like this. We put the force on the y-axis, we put separation on the x-axis, and we'll mark a couple of points of interest. So here we've got 0.5 femtometers. Over here we'll do 3 femtometers. And we'll label the two sides of our y-axis with descriptors. So if it's above, this is repulsive. And if it's below, it's attractive. So at less than 0.5 femtometers, we've got very strong repulsive force, which goes down very rapidly. Then it curves back up and goes to 0 at 3 femtometers. Yes?
Width is at 0.5.
Huh?
Width is only 0.5.
At 0.5, then it goes through 0.
Oh,
Yeah? But what will happen there is, imagine that's 0, but would the electromagnetic force of repulsion be 0? No. So that will be repelling. So if it's at 0.5, then the electromagnetic force will have a repulsive force on there, which will push it this way. Yeah? And then you can see the kind of shape that it creates. It tries to keep it within this zone. Yes? 10 to the minus 15. So 1 femtometer is 10 to the minus 15 meters. Now, in a different color, I'm going to draw roughly what the electromagnetic force looks like. So the electromagnetic force would look something like that. So blue is the EM force. And the black is the strong nuclear force. So between two protons, the electromagnetic force is always repulsive. It's never attractive.
So, after the resistance is greater than 3 femtometers, then what happens?
Then the strong nuclear force doesn't apply anymore. So the protons repel. So if I have two protons that are not inside a nucleus, one proton separate here, one proton separate, several femtometers apart, they will just repel each other.
And the nuclei are still the nucleus.
They won't form themselves into a nucleus. We can force them together and make them form a nucleus, but just by being far away, the strong nuclear force will not bring them and form a nucleus.
So
But if they're already a nucleus, the strong nuclear force will keep it together.
as you said, if there's like a big atom or big molecule, then they're way more separated. So how is that nucleus there?
Right, we will explain that now. So to understand, and this explains why we have neutrons in atoms, in nuclei, and why, if you look at a periodic table, at the beginning, hydrogen, there's no neutron. Then you have helium, 2 protons, 2 neutrons, equal amount of protons and neutrons. Lithium, 3 and 4, almost the same still. You look at the rest of them, beryllium, boron, carbon, nitrogen, oxygen, etc. You'll see that a lot of them have basically similar numbers or almost the same number of protons and neutrons. But you get heavier and heavier, and then what happens is you start to see that the number of neutrons overtakes the number of protons. Yeah? So, if we imagine what happens. Let's start with one proton and another proton. These two protons are repelling each other through the electromagnetic force because they're both positively charged. But they're also attracting each other because they formed a nucleus, they're attracting each other through the strong nuclear force. Now, what I'm going to do is I'm going to add more and more and more protons. Hypothetically, this can't actually form a nucleus in real life. So here's more protons. And I'm going to label this as proton A and proton B. Now, proton A is repelling every other proton that I've drawn, all the way to proton B. So every single proton there has added a significant amount of repulsion to every other proton. But proton A and proton B are so far apart that A and B are not attracting each other through the strong nuclear force. A is attracting these adjacent ones through the strong nuclear force, but the strong nuclear force can't attract B. But all of these are also repelling. All of these are also repelling. So now if we change our nucleus, we got some protons. Now we randomly turn some of these into neutrons. And I'm going to try to get roughly equal but maybe slightly more neutrons, because the neutron number does, for larger nuclei,